Welcome everyone to another seminar talk. So today is the Ricci Bounce Day, and I'm delighted to introduce our first speaker, Professor Sturm from University of Bonn, and he's going to talk about distribution valued Ricci bounds.
Yeah, thank you very much. It's a pleasure for me to be here in this beautiful program, and it's really a week full of activities which I encountered here. So I hope you are still able to listen to other ideas. What I present today is a rather comprehensive talk which contains a number of ideas, and I would like to regard this as an invitation for various of you to look a little bit deeper in this or that direction. So there is analytic challenges, there are, I would say, interesting geometric ideas and also probabilistic techniques. So just regard this as an invitation to continue to work a little bit more in a similar direction. So I will first speak on heat flow and ground motion on metric measure spaces, curvature dimension condition, and probably many of you have heard that, and if not so, they will certainly learn everything in this respect in the lectures by Nicola. Then I will go on and speak on distribution valued Ricci bounds. So this is a kind of extension which I want to promote today, and a particular application then will be to heat flow with Neumann boundary conditions on non-convex domains, and some ideas behind that with time change and convexification. But actually also this part has some interesting ideas which applies to convex domains. Now, in some sense, what you do if you do optimal transport, these things, you say, okay, I have a metric measure space which has curvature dimension condition, everything is fine, I can pass to a convex set, everything is fine as before. That's true, but it's better than before. And you cannot quantify this if you do not really establish additional tools. And also this is a kind of invitation to look a little bit more on how much you can improve results if you have not just convexity in the sense of a lateral boundary which looks like a half space, but really convexity in the sense of strict convexity, where you feel curvature of a boundary. And what I also want to make a propaganda for is that everything you should try to feel in terms of metric quantities. Yeah? So boundary curvature and so on. I would not really believe that this is the best possible answer. I'm quite sure that the young gifted people here in the audience will present much better definitions within the next years, but maybe this is the first definition which provides non-trivial results. Okay, this is, oops, sorry, this was the wrong button. This is essentially based on a paper of mine which appeared in GAFA some years ago, not too long ago, and which is based on a number of joint works with various co-authors, partly also here in the audience. Then a very strong input comes from a paper from Bangxian Han and myself. And I also want to point out that there is a follow-up paper of this theory, which is by Erba, Rigoni, Tamanini, and myself. But I really do not go into these details, so this is then maybe even too complicated for such an introductory talk. Very brief introduction to heat flow and ground motion on metric measure spaces. The work of important people, including Brené, Robert McCann, and many others, led us to the understanding of metric measure space and its relation to heat flow. So heat flow is one of the most important analytic concepts, optimal transport and heat flow. These are very important concepts on metric measure space to understand that. For the heat flow, of course, you have to start with something, and the starting point is the concept either of an energy, and when you study the gradient flow of energy in L2 space. This is what you could call the traditional approach, or you study, following the ideas of Felix Otto and co-authors, you study the gradient flow for the Boltzmann entropy in Wasserstein space. Both have advantages and come with some challenges. What I call the traditional approach, heat flow of energy in L2 space, this has the advantage that this is in some sense what people did since decades. L2 space is clear and a nice object for energy whenever this is defined. This is convex, but you have to define it. And this is a priori not so obvious on metric measure space. So what one would like to regard this as a kind of integral of a gradient squared. And again, by work of people also here in the audience, Ambrose Chili-Savary and many others, including also the Finnish school, which started in this direction, Chige, Jamugalian, and others, it became clear how one should proceed. The easiest way to make a short introduction is you start with a, let's call it pointwise Lipschitz constant, you square it, this is roughly speaking the modulus of a gradient, but it's not really the object you want, because this is not necessarily a lower semi-continuous function on L2 space. And whenever you want to build up a reasonable function and analytic concept, this energy function has to be L2, has to be lower semi-continuous. Okay, what do you do if you have something which seems to be the right object, but which is not lower semi-continuous? You make it lower semi-continuous. Just take the lower semi-continuous envelope, which is called relaxation in calculus of variations, and you end up with this object. It's quite important and very helpful that this also has a pointwise representation in terms of a so-called minimal weak upper gradient. I'm sure that in the lectures by Nicola, you will learn about that. For this short introduction, I won't go in detail, but also this is quite nice, that this is not only a relaxation in L2 space, but this is an object which also allows for a pointwise definition, pointwise in the sense that at almost every point you have something. And the disadvantage in some sense for the Boltzmann entropy, of course, is, okay, you can define the Boltzmann entropy without any problems, but okay, it's not so clear what is a gradient flow in Wasserstein space for such a functional. Is it at all semi-convex? Yeah, if you want to define gradient flow, it's always good to have a convex function or a semi-convex function. And Ambrose Chili-Savary then finally proved that if the latter is okay. So sorry guys, in the remote, I don't start from the beginning, I continue here. So what we defined as a synthetic definition of, let's say, non-negative curvature is that the Boltzmann entropy is convex. Convex in the sense that if we consider this function along geodesics, then this is convex. And convex, just the usual midpoint property. Entropy in the midpoint of a geodesic is dominated by the convex combination of entropy at the endpoints. And K-convexity simply means you have a quadratic in the distance correction term with a K in front. So this is just the, if you write down what convexity on the real line means in terms of an integral condition, this is exactly what comes out. So this was the definition of K-convexity, and of course, there are some subtle issues which are important in order to really make the theory to a very powerful theory. for instance, this is not required along every geodesic. This is required along sufficiently many. So for each pair of points, there is a connecting geodesic. So this is exactly what makes it stable, this formulation. Whereas for the gradient flow, a priori, we would, of course, be happy if it's convex along every geodesic and so forth. So this is what I do not discuss in today's talk. And you see here, we have a metric measure space, which has two ingredients, for distance and for measure. And here, the measure enters the definition. So for Boltzmann, entropy uses the metric, and the distance along which we use for defining the geodesic, this uses the distance. So we have these two ingredients. One defines as the geometry, and the other one for functional, which we study in this space. And just an example why one could believe in such a property is if you look on the round sphere, the transport from this green uniform distribution to this green uniform distribution. So you have two masses which are concentrated in rather small regions. And here with the sign convention, it means if you concentrate a measure in a small region, the entropy is very big. And now, according to the geometric structure of a round sphere, the set of midpoints is larger than the set of endpoints, because you have positive curvature on the sphere. So this set of possible midpoints is larger, and therefore it's no surprise that the entropy is smaller. It spreads out, and the entropy really looks like a parabola in this space. And it's exactly this parabola which provides you with this curvature 1 of the round sphere, or times normalization constant. So this is what is the definition of entropy. Now we switch for the rest of the talk to an important subclass of the so-called infinitesimal Hilbertian spaces, where the heat flow is linear. I told you that the heat flow can be defined as gradient flow of entropy and energy. Both are equivalent if we have K convexity, but they still might be nonlinear. Yeah, for instance, on a Finsler manifold, still this equivalence is true, but the heat flow is a nonlinear flow. The Laplacian is a nonlinear operator. Energy is not a quadratic functional, and the heat equation is, or heat flow is not or heat operators are no linear operators. So we always assume for the sequel that the spaces are infinitesimal Hilbertian, which means by definition that the energy is a quadratic functional, or equivalently that the heat equation is linear. This corresponds to the fact that the tangent spaces are Hilbert spaces. The energy is essentially the metric tensor on the tangent space. And for these spaces, one can prove, and this was done actually in this form by Ambrosi, Gillet, Savary, that the K convexity is indeed equivalent to the so-called Bakry-Emery inequality or Bochner inequality. So in this shorthand notation of Bakry-Emery, gamma 2 is larger than K times gamma. I don't go into details. Those who know about gamma calculus, they see this. And in explicit terms, this just is the Bochner inequality without the dimension term. And now we have two completely different approaches. So this starts with this Lagrangian picture, entropy, convexity, Wasserstein, geodesics, and so on. And here we have an Eulerian picture with an energy, with a heat equation as a PDE. And we started with the energy as a gradient flow in L2 space, and another differentiation leads us to a third order differential inequality, which is the Bochner inequality. And both this K convexity here and the Bochner inequality with K here are abstract versions of the formulation that the space has curvature larger than K, Ricci curvature larger equal K. Actually, this kind of inequality, this is quite well known. So Bakry and Emery developed their theory already in the 80s, starting from Markov semigroups, and there's a huge theory. They had been mainly interested indeed in doing infinite dimensional calculus, equilibrium rates, and so forth. There is also a dimension-dependent expression where there is a 1/n times Laplacian squared here. And for the sake of simplification, I only have written now the dimension-independent case. And then there are two other inequalities which more emphasize the dynamic aspect. Again, one in the Lagrangian picture, one in the Eulerian picture. Let me focus on this one and just take p equal 2 here. I have written this for more general p. The gradient estimate and the Bochner inequality, they are known to be equivalent since many years. So this is a simple two-line argument. Just differentiate this forward-backward semigroup, and then you see that the Bochner inequality allows you to prove this gradient estimate and vice versa. Differentiating the gradient estimate at time equals 0 gives you the Bochner inequality. So this is very easy that the last two, at least with p equal 2, are equivalent. P equal 1, this is a deep property, then that this is also equivalent. This is the so-called self-improvement property. This is a quite funny property, saying if you have a certain function inequalities, then it automatically gives you a stronger one. Yeah, because you apply this not only to u, but to u plus f of vw, and you play around and so on, and finally you have a better inequality. This is the so-called self-improvement, which allows you to pass here from the p equal 2 version to the p equal 1 version. The other way around is just Hölder inequality. This is trivial. And also in the Lagrangian picture, we have a dynamic version, namely the contraction in the Wasserstein distance. And intuitively, it's clear if you have a k-convex functional in L2 Wasserstein space, and if you define the heat equation as gradient flow, you would expect if I have a k-convex functional, then the starting at two different points leads to a flow which contracts with rate k. This is true in the infinitesimal Hilbertian case. It's wrong on Finsler spaces, and we have still no good replacement on Finsler spaces. Yeah, for this property, this assumption is really crucial. We have a reasonable replacement for that on Finsler spaces, but not for this property. So even if intuitively it's clear that k-convexity of a functional and k-contraction are the same, technically this is by no means clear. It is clear if an underlying space itself is infinitesimal Hilbertian. If you look on this as a question, abstract metric space, regard the Wasserstein space now as your metric space, if this space is infinitesimal Hilbertian, also this is known, but not in general. Okay, now let's go on. These are not the only equivalences. I have shown you 4. There are 5 others. Actually, these are more than 5 because at some assertions there are 2 inequalities. So these are at least 7 inequalities, each of which is equivalent to synthetic lower Ricci bound. Now, if I have here, for instance, inequality here and there, you see left-hand side and right-hand side, this is essentially the gradient estimate. Gradient PT estimated against PT of gradient. And now we switch something in between. And both with something in between less than the right-hand side is equivalent to lower Ricci bound, and the lower estimate is equivalent to lower Ricci bound. So there is a whole slew, and here I have simplified further. I have, in some sense, dropped the k. Anyway, I have dropped the dimension because things get out of control for this survey. But most of these things also allow a version with a dimension. As I mentioned, this local punctuary is just an improvement of a gradient estimate. There is a version where instead you have here kind of an entropy inside. Quite nice properties are the so-called dimension-free Harnack inequalities and log Harnack inequalities due to Feng Yu Wang, which are dimension-independent extensions of a classical parabolic Harnack inequality. You see here there is one single inequality at the end of a day in some sense. This also could be used as a characterization of non-negative Ricci curvature. The most elegant, from my perspective, and simple characterization, and also very deep characterization, is this in terms of Brownian motions. One can characterize a space with non-negative Ricci curvature by this important property that wherever you put your starting points, you can construct pairs of Brownian motion which never increase the distance. This is equivalent to non-negative Ricci curvature. And actually this property is indeed used also by people modeling financial markets and biological systems and so forth. So Ricci curvature is a kind of control how divergent your evolution is. And non-negative Ricci curvature says not only on the level of expectation or distribution, you do not increase distances, you can even model this on a pairwise level. Yeah. No, just infinitesimal Hilbertian. What do you mean with existence of heat kernel? No, this is then true for almost every pair and so on. So if you cannot start with deltas, you do it in distributions. You start with distributions. Now you say for any pair of distributions, absolutely continuous, this does not increase the distance. If you can start with deltas, it's true for deltas. If you cannot start with deltas, yeah, you smear it out. But a priori, no restriction. No, this is a refinement of a non-expansion of Wasserstein distance. It's a very strong refinement, but it more or less requires nothing. Yeah, I like this because at least for those who attended one lecture in stochastic processes, they have a certain feeling what this could mean. And for people in modeling, this is a very natural condition. And also this is a very natural condition if you think in terms of going to a discrete space, both discrete in time and discrete in space. Yeah, because then you have a random walk, and again, you expect that it should not increase distances. Of course, you have to be a little bit more careful and so on. Okay, this was my very short introduction, the first part, which I wanted to address to an introduction to the field for those who did not go to all the other lectures presented so far here. Now I want to address once again these challenges. Uniform lower Ricci bounds are preserved by passing to a bounded subset with normal boundary conditions if this bounded subset is convex. You see this immediately in the optimal transport picture, because optimal transport picture says whenever you have two distributions, you find a geodesic, along this geodesic you have convexity of entropy. If you now are in the convex subset, your geodesic which you consider is the same as before. This is the convexity of a domain. So you look on the same geodesic, you have only less constraints which you have to check because you only have distributions in your space. So therefore it's clear. It's also quite easy to see, this is not obvious, this is indeed a theorem, but it's rather clear theorem from the intuitive interpretation. Whenever you have non-convexity, you have no chance. Now, because if you have a non-convex domain, you choose a probability measure here, you choose a probability measure there, and then in your domain, you want to connect these probability measures along geodesics. Okay, how does the connecting geodesic look like? It goes that way, again, here. And if you have a smeared out distribution here, a smeared out distribution here, you have a distribution which has not n-dimensional support. The support is living on a lower dimensional measure. The entropy cannot be finite. This is, in some sense, the proof by picture. There is also a proof by epsilon delta. So whenever you are in this infinitesimal Hilbertian situation, and if you can switch between gradients and gradient estimates and optimal transport, this is a fact. And therefore, if you want to okay, from my point of picture, okay, let me begin a little bit with a larger picture. So what I have in mind is I have a space X on which I verify all these conditions. And then I give myself a subset, open, closed, can be discussed later. But let's say if a boundary has no mass, this at least should be satisfied. And then I want to study this Y as my new metric measure space. And with this Y as a metric measure space, there comes an energy and an entropy, and therefore also a heat equation. And this heat equation in classical terms is the heat equation generated by the Laplacian with Neumann boundary condition. This is this general message for those who are not familiar with Dirichlet forms and all these things. Whenever you pass to a subset, or if you construct a metric measure space on a subset, if you do not discuss any further constraints, what you obtain will be the heat equation with reflecting or Neumann boundary conditions. If you do not have completely crazy boundary and so on, whenever you can give a meaning to the Neumann Laplacian, this will be the object. And for this heat equation, which I call, how did I call it? Neumann Laplacian. Yeah, okay. I think it's a reasonable name. You don't like the name?
Oh, no, I just didn't understand.
Okay, yeah.
Now I understand one how to like it.
Yeah.
So you're saying this is the gradient, the Neumann Laplacian generates the gradient flow of these other groups.
Right. For me, the alternative way would be to speak of a Dirichlet Laplacian, which is very natural if you start with stochastic processes, with Dirichlet forms, because then you have no regularity issues to start with. But if you start with metric measure space, the most natural heat equation on a subset is the heat equation with Neumann boundary condition. This is the equation which comes out of a new metric measure construction. Okay, and as I mentioned, one of the challenges now is can we do anything for non-convex domains? Yeah? It seems plausible that there should be something, but it's certainly not a uniform lower Ricci bound. And so one way is to approach this step by step, replace uniform Ricci bounds by a variable Ricci bound with a function. Then maybe it's also better to pass to measure or to a distribution. And this is what I'm aiming for. Okay, my time is going on. Matthias, sorry for that. So we switch the function stuff and we go directly to the metric measure space. So let's assume that we have a metric measure space, infinitesimal Hilbertian, and then we define Sobolev spaces based on the L2 gradient. So this is just for insiders. And what I define is then the W11 space, where I use the L2 gradient for approximating sequences, and I want that the L2 gradient, roughly speaking, has a norm bounded in L1. I do not want to introduce an L1 gradient because at the end of the day, I want to stay in the L2 theory. If you are if you already would have all the results from RCD theory at hand, it would make sense to speak of P independent, but we want we are one step earlier. Yeah? We have spaces without curvature condition right now. And so we define the W11. We have a -1 infinity as the dual of it. And yeah, maybe I directly go to the, no, okay, this was too far. What we need is then that the energy extends from a bilinear form on W12 cross W12 to a bilinear form on W11 cross W1 infinity. So in one space, we make it more restrictive, on the other more flexible. And the same does the gamma operator here. And this allows us also to define a Laplacian as an operator from W1 infinity to W minus 1 infinity. This is not that surprising. These are just the objects we would like to see. We are interested in these spaces mainly because this is then our essentially what we have in mind is we want Lipschitz functions to see here. And oops, wrong direction. And then we formulate the Brockner inequality with such a kappa. So kappa, which plays now the role of our Ricci bound, this is what we want to have, is a distribution in W minus 1 infinity. For many purposes, this seems to be a quite reasonable class. So it's essentially what allows us to develop a theory without too much complications and to include a huge number of additional examples. We start with a Bochner inequality in its sharp form with the so-called Bakry-Emery or Bochner inequality 1, which in this form reads as follows. So in shorthand notation, it's just that the Laplacian of a modulus of a gradient minus this guy here is larger than the modulus of a function times this distribution. And the precise interpretation is we have this pairing here with a distribution W minus 1, and we have here this pairing grad f modulus times phi. Both are in W12, and therefore the product is in W11. That's the point. We have a product here, and we have to keep under control this product, and this is W11. And therefore, this pairing with W minus 1 infinity makes sense. And with such a kappa, we can define a bilinear form. It's the classical Dirichlet energy plus Fg kappa. Again, this is meaningful. And if you think in yeah, okay, let's simply say this is meaningful. And we have a semigroup associated with that. I will explain the semigroup a little bit more on the next slide. And the most important result here in this context now is that the Bochner inequality indeed is equivalent to a gradient estimate. So we have a gradient of a semigroup is dominated by some Schrödinger semigroup applied to the gradient. I should explain this Schrödinger semigroup in a minute. So if kappa were just a constant, this Schrödinger semigroup is simply e to the minus kt times heat semigroup. I'm lost a little bit. Here? Sorry. Here? It means the gradient of a function in the operator domain lies in the form domain. Yeah. A square root of a gamma operator. No. Gradient of functions in the operator domain lies in the form domain. This is exactly what is needed in order to make this. And this is okay. In some sense, you need conditions which allow you to write down these things in a meaningful way, and you need conditions which are preserved under your semigroup. Now, this is always the game.
What would be some typical example of kappa, like when you have
Yeah.
space with boundary?
I just come to that. So, main example. It starts, the main example for such a Ricci bound is the Laplacian of a Lipschitz function. And for a geometry, this enters, for instance, think of dimension 2, make a conformal change of your metric with a Lipschitz function, and the new Ricci curve, which is the old one, plus the Laplacian of this function. And it's typically not in any nice class. Yeah, but whenever you make this conformal change with a e to the psi as a weight function, the new Ricci is the old one plus Laplacian of psi. And whenever you take a bounded Lipschitz function, this is now within this theory. And this is beyond every Kato class, LP class, and whatever. Laplacian of psi for a Lipschitz function is only in this space, and there is no better space. And with a boundary, whenever you have a bound on the second fundamental form, then the surface measure will be also in this class. Okay, I have to speed up. I'm moving in the wrong direction, I guess. No, completely in the wrong direction, sorry for this nonsense. This is what I also wanted to show you. If this is our main example, that for kappa is the Laplacian of a Lipschitz function, and essentially this is one-to-one, yeah, because the Laplacian and maps from W1 infinity to W minus 1 infinity in the green operator for Fourier out. And if this psi were a smooth function, then this semigroup, which I have mentioned, is just the Schrödinger semigroup, and many of you know the Feynman-Katz formula, which says if you have a potential, then this potential pops up here in the exponential, and you integrate this. Now the psi typically is not in the domain of an operator, the Laplacian of psi is not typically a well-defined object, and the name of a game then is to give a meaning of this object here. And here Fukushima decomposition helps us, because Fukushima decomposition tells us that we can replace this object, the Laplacian of psi, by something which is meaningful. Namely, Fukushima decomposition says whenever this is function in the form domain, it can be written as a martingale, which essentially contains the gradient of psi, but which requires no further differentiability, plus a term which is an abstract replacement of this guy. So in other words, if we want to give a meaning to this object in abstract terms, we can define it in terms of these other terms. Function and first derivative allows us to define a replacement of a Laplacian. And this is how the semigroup at the end of the day is defined. I skip that and go ahead a little bit more. So this is now, in some sense, these main applications. In many cases, we have a metric space, and what is called time change now simply means in probabilistic terms that we pass to a new process where we have the same measures on the path space, but we run along the paths with different velocity. In analytic terms, this simply means you have a Dirichlet form and you take the same energy, but you look on this on a different L2 space. You just give a new way to L2 space. In operator terms, this means you multiply your operator just by a function. This is the time change. Function times operator. And in metric measure space terms, this is a little bit more tricky because you change the measure and you simultaneously change the distance. Therefore, metric measure space allows for an explicit definition of that, but this is not the most natural picture to start with. What is important is, and this is the result of Bangxian Han and myself, developed in a number of papers, separately and jointly. If our old space satisfies a Baku-Emery condition with reasonable function k and a finite dimension, then the new space also has a Baku-Emery condition. And indeed, this is sharp. So this is the exact formula on Euclidean space. And this formula for the new Ricci bound involves the old one, the gradient of psi, and this abstract Laplacian of psi. And therefore, if we have a psi, which is, for instance, just a Lipschitz function, it's good to have extended the setting of curvature bounds, because we really obtain distribution valid bounds. Most of you know the formula for the curvature bound, which is a so-called drift transformation, where you obtain a new curvature bound as the old one plus the Hessian of psi. Here it's not the Hessian, it's the Laplacian of psi, which has quite a number of advantages, because Laplacian is much easier to manipulate. And controlling the Laplacian also is easier from a technical point of view, but it requires finite dimension. Without, in the infinite dimension case, there is no counterpart. So this is really a condition which uses the curvature dimension with both parameters k and n. And now there is one result, and probably I will not have enough time to go in all these details. This summarizes roughly what will happen on the next slides. If I have a subset Y of my space here, which has a lower bound for the curvature of its boundary, in a sense which I did not even define so far, then the restricted space has a distribution valid Ricci bound, which is the old one, plus lambda times the surface measure of this boundary. And lambda is the curvature bound on the boundary, and I define curvature bound of a boundary in metric terms. The intuitive idea is that a convex set is more or less the same as a level set of a convex function. Yeah, and a k-convex set should be a level set of a k-convex function. This is the idea behind it. And now instead of k, we have a lambda. So we think of a lambda convex function. Lambda is just a lower bound for the convexity of my function, which I use to define that. Maybe I should jump to this definition. Here we say that lambda is a lower bound for the curvature if this function v, which is just the distance function from the boundary, is lambda convex. I could also take the distance function positive counted outside, negative inside, but I check this condition anyway, only in the exterior. And it turns out that for Riemannian manifolds, this is equivalent to a lower bound on the second fundamental form. And since I'm always trying to make propaganda for metric geometry, I should have at least one example also beyond the Riemannian case. If I have an Alexandrov space with lower bounded, with non-negative Ricci curvature for simplicity, and if I have an exterior ball condition with a certain radius r at each point, then the negative inverse of this radius is a lower bound for the curvature. This is exactly this intuitive picture which you have with curvature bounded by these functions. And what is crucial now, this is this theorem. This is what I want to tell you at least. How do we approach this? If we have such a set here, then we go to a weighted metric and make it convex. And this is one of these nice consequences of this definition. So we have, first of all, this distance function from the boundary. Let's say, maybe it's nicer to think of a signed distance, but it's not so important. And then we go to a new metric, which is, if you think in terms of metric terms, you multiply the metric tensor by e to the psi, where psi is negative curvature times distance function. Yeah, if you have negative curvature, you should make it more costly here. Yeah, and this exactly does the job. With this distance, okay, you add an epsilon, yeah, forget this epsilon, this is just for technical reason. With this distance, the set now is convex. This is just metric geometry. You prove the convexity by a gradient flow of geodesics. So if you start, if geodesic would run out, it turns out it's too costly to go outside. And now you have a convexity, and with a convexity, you can make the calculus, which you have seen before, gradient estimates and so far. We know how curvature bounds change, and then later on you have to go back. Okay. Oops.
Do you have to have any assumptions that say y is connected?
Okay, I think of a connected set, yes.
Okay,
yeah. And also with this convexification, there is a notion of locally convex, yeah, because if you think on a set on a torus, we change the boundary, okay, anyway, we do not change the boundary, but we change the geometry locally in some sense, yeah. A large set on the torus still will be not convex, but if a optimal transport in the neighborhood of a boundary tries to exit, it has no chance. Okay, I wanted to show you one picture which in some sense is important. Oops, no, where was this? I have two. Okay. But I think this picture is very instructive. So think of Euclidean space, yeah, and now we want to study heat flow on the exterior of a ball. This is in some sense the prototype. What do? We make a conformal change of our metric. So in classical Riemannian terms, this is just conformal change. And if you want to make a picture where this is isometrically embedded, this conformal change would say, okay, now I look on this geometry. I have made a conformal change which pushes the geodesics away from this boundary. if I'm start from outside. And actually, this conformal change is exactly what I would obtain with my distance function times curvature. And the boundary at the end of a day is a totally geodesic set. Yeah, it's like the boundary of a half space. And the nice thing is, I have a convex set here, and also the complement is convex. And this is where I want to aim at. Yeah? Because the same construction I also can apply to the interior. I do the construction, make a conformal change, and then I see an additional term. Because with this, if I make the passage from the whole space to the subspace, I make on this level. And on this level, I lose almost no information. If I make reflecting Brown motion, the gradient estimate is as good as possible. Of course, in 2 years, there is somebody who also improves that. But at the moment, I think reflecting on a totally geodesic subset, this is the best possible, what we can achieve. There is no curvature, neither if you do it in the set nor in the complement. And now, here, in some sense, we separate these two sets. Yeah? Either you started inside, when this is your space, or you started outside, when this is your set. You consider reflected Brown motion, you have kind of optimal results, and then you continue with this game. What you have to do then is making this time change in a reverse order. And okay, sooner or later, then what you have to discuss is the Laplacian of a distance function. Because the Laplacian of this weight function enters the picture. To start with, this is no problem because you, at least in a smooth setting, you can extend your distance function to a signed distance function. Then if you have a smooth boundary, it's in the domain of a Laplacian, let's say if you speak intuitively. But if you go back, there is no exterior. And the Laplacian certainly is not in the distance function is certainly not in the operator domain of a Neumann Laplacian, never. And therefore, a distributional valued part appears, and this is the curvature of a boundary. I try to give you these results, then where does it show up? Yeah, and this is then this term. We have this Laplacian with this Neumann Laplacian now applied to psi, but psi is this function which makes our time change, which is essentially the distance function from the boundary. And here we really need a distribution. Without that, it cannot be true. And this is where we finally end up with this construction. On this last page, there is a number of hidden regularity, which I did not mention. With a number of hidden regularity, which is satisfied in the smooth remaining case, but it's certainly not satisfied without any extra assumption on general spaces. And therefore, what I claim, this is an approach to regularity and so forth. I would not claim that this is the most efficient. On remaining cases, this leads us exactly to the, I would say, best known results. And I was also amazed to see that this gives some nice estimates. Let me finally give these two examples. So let's have a look on the complement of a ball. This is where I started with. And you would have no chance to prove gradient estimates with classical terms. And what we end up with is that the new gradient estimate looks as follows. So it's the gradient of heat semigroup divided by the semigroup of a gradient. And you get a e to the constant time, which is what we know, plus a e to the constant square of time. So this is now the contribution, the singular contribution of a boundary, of a curvature of a boundary. I don't know whether this is the best possible, but let's say without the square root of a t, such an inequality cannot be true. And I did not optimize on this constant, so this would be a challenge for other people. And sorry, I'm always wrong with this. And now on the ball, where we already know gradient estimates, we say gradient estimates are as good as on the plane. But if we do this more precisely, we would obtain some extra information. We would get e to the minus something. And with each of a minus something comes from the positive curvature of a boundary. And it allows us with these tools also to make an estimate of a spectral gap on the sphere in terms of a curvature of a boundary. Just this concept might be new. Of course, we have a compact space. We expect that there is a positive spectral gap. Typically, we estimate it in terms of a size. And now we just take the curvature of a boundary, the total curvature, and say, okay, if there's enough curvature of a boundary, the lambda 1 has to have a lower bound. Okay, I have to stop. Thanks for your attention.